so this is problem number 1 off of the worksheet titled Net Torque and Rotational Acceleration. Okay, so I'm going to take this text to make some room to solve this. I'm going to delete the text. You guys all have the problem in front of you. I'm going to make the diagram nice and big. So we have this solid cylinder, and we're given the mass of the cylinder is 5 kilograms. So the first thing I want to do is calculate the rotational inertia. Even though the question doesn't ask for it, let's calculate the rotational inertia of the cylinder. So what's the equation for a solid cylinder or solid disk? Rotational inertia for a solid cylinder or solid disk equals 1/2 mr squared. And you don't have to memorize those, because there's like, what, 8 of them I gave you. Is it a hoop? Is it a solid cylinder? Is it a solid sphere? Is it a hollow sphere? So I'll give you the equations. You don't have to memorize the rotational inertia equations. So you go 1/2, the mass of this cylinder is 5 kilograms. The radius is right here, but you want to put that in meters. 0.12 meters. So we get a rotational inertia of 0.0144 kilogram meter squared. So we're going to use this in a moment. All right, now, the first question that the problem asks for is the net torque on the wheel, or on the cylinder. So how many forces are acting on this cylinder? 3. We have a 6 Newton force, a 4 Newton force, and a 2 Newton force. And then these other 2 values are distances. Okay. Do these 3 forces agree or disagree in terms of which way they want the cylinder to rotate? They disagree. So which way does the 6 Newton force want? Counterclockwise. So let's say that's plus. That's the official sign convention. Counterclockwise is plus. Okay, the 4 Newton force here wants clockwise, which we'll say is negative. And then the 2 Newton force wants clockwise, which we'll say is negative. Now, how do you calculate torque? The basic equation for torque is force times lever arm, where R is the lever arm. And the key thing, the force and the lever arm must be perpendicular. Now, this is a nice situation, because if you look from the axis, which is right here, here's the axis, up to the 6 Newton force. What's that distance there? It's the radius, which we're told it's 12 centimeters. And it's perpendicular, right? So the torque for this guy, we're going to go force, which is 6 newtons, times the distance, which is 0.12 meters. So that gives a torque of positive 0.72 Newton meter. So we got the torque for the 6 Newton force. Now, come over here to the 4 Newton force. Same thing. So we're going to go torque equals force times lever arm, 4 newtons. Now, what's the distance for the 4 newtons? 12 centimeters, because it's still the radius. If you go from the axis out to the force, perpendicular, that's simply the radius. Okay? So this is going to be 0.12. Those are perpendicular. So this is a torque of negative 0.48 Newton meter. Okay, then lastly, we have this 2 Newton force here. So that's going to be torque equals 2 newtons. Now distance to the 2 Newton force, it's right here. And it's a perpendicular distance. From the axis over to the force is 5 centimeters, so we go 0.05 meter. So this is going to be negative 0.1 Newton meter. So we've calculated the 3 torques. We have this guy, we have this guy, and we have this guy. We've taken into account the sign convention. So how do we find the net torque? We add them up. There, let's make some room. Actually, I'm going to shrink this down now. Okay, so we go like this. We're going to sum the torque. And by the way, guys, the summation of the torques is the same thing. It's the exact same thing as net torque. Net torque and summation of torques, same thing. So we have 0.72 Newton meter minus 0.48 Newton meter minus 0.1 Newton meter. Okay. What's the sum of the torques going to equal?
0.
Not 0. I alpha. So look, that's the equivalent. That's the equivalent of F net equals MA. At this point, like if you were paying attention last week, which I hope you were, the thing you should realize is that F net equals MA. That's for linear situations. For rotational situations, it becomes torque net equals I alpha. Those are the same equations, just one's linear and the other one's for rotation. All right, so how do we answer the first question? The net torque is, so you add this all up right here, that's the net torque. It comes out as 0.14 Newton meter. Okay? Oh, and then which way is the net torque? Is it clockwise or counterclockwise? Counterclockwise. So which way is this torque going to be directed? So what you do, you take your four fingers. When your four fingers curl counterclockwise, which way does your thumb point? Out of the page. And I should add, you have to do it with your right hand. If you do it with your left hand, you'll get the opposite answer of what you should. Okay? So this is 0.14 Newton meter out of the page. All right. So the first thing we did, we calculated the rotational inertia. The rotational inertia is 0.0144. We plug that in right here. So now we can say this. Now we can say 0.14 Newton meter equals I alpha. So alpha is going to be 0.14 Newton meter divided by 0.0144 kilogram meter squared. And then this gives the angular acceleration, which we get 9.7 radian per second squared.
With the second square.
Okay, good. So the units. Let me show you how the units work out. So the units for this, so if you look at what we did here, so we have Newton meter over kilogram meter squared. So here's what happens. So Newton meter over kilogram meter squared. Now remember, what is a Newton? A Newton is actually kilogram meter per second squared, and then times a meter over kilogram meter squared. So here we have meter times meter, which cancels with the meter squared, right? Kilograms cancel, and this is 1 over second squared. And radian, the thing to know about radians, it's a counting unit. It's not a unit the same way that meter is a unit or second is a unit. Okay, last question. What is the tangential acceleration for a point on the... Come on, computer. So how do we find the tangential acceleration? What's the equation for it? Angular acceleration times the radius. So to get the last part, we're going to go 9.7 radians per second squared. The radius out to the perimeter is 0.12 meters, which gives an acceleration of about 1.2 meter per second squared.